Welcome back to the class on a semi-connected drives. In this class, we are going to discuss about the first quadrant operation of a DC shunt motor. The first quadrant operation is nothing but a motoring operation, where the voltage and current is positive, nothing but the power is flowing from the supply to the motor, so the motor will be rotating in a one direction. Here, one important point is that the input is a DC voltage. We are keeping a one circuit between the DC supply and the motor so that it is giving a variable DC voltage to the DC motor. That's why we are calling it as a DC to DC converter. Now we are going to see the how we are getting the first quadrant operation of a DC shunt motor. So this is the circuit diagram of the first quadrant operation of DC shunt motor, nothing but a step down chopper also. So this is the switch, nothing but a control switch. This switch we can replace with the MOSFET or the IGBT. Whenever we are given the base voltage to the switch is on. If you withdraw the base voltage, the switch will be off. This is the input voltage VDC. This is the load. This is the field winding of a DC motor. This is the positive direction of the load voltage. This is the positive direction of the load current. This is the diode which is connected across the load. This diode is nothing but a freewheeling diode. And the current is passing in this direction that we have taken as a positive direction of the freewheeling current. That is denoted by the IF. Now we are going to see the operation of the circuit. How exactly it is given the motoring operation so that it will give the variable speed of a DC motor. Here the input voltage is the DC voltage. So first we are representing the input voltage. So we have taken the y-axis. Next we have taken the x-axis. On the x-axis we have taken the t. On time. See here, we have taken the one dotted vertical line on time of the switch. One more dotted line off time. This time is nothing but off time of the switch. This is nothing but a one time period. Like that, we have taken the one more time period. Now, this is the DC voltage. So, we have to represent the input voltage in the graph. So, the DC voltage is nothing but a constant line that we represent with a red line, that is the DC voltage. That is Vs, nothing but source voltage. See in the circuit diagram, the switch is on. This voltage is connected to the armature of a DC motor. So the current is passing from the input voltage, switch, armature, again return to the source. In this interval, the current is changing from the minimum value to the maximum value because we have taken the load current as a continuous load current. Which is on, the load voltage is equal to the supply voltage. Now we are going to draw the output voltage. So in this interval, the switch is on. Once the switch is on, the output voltage is equal to the VDC. This is the VDC. When the switch is off, already there is some amount of energy will be stored in the armature of a DC motor that will be circulating the current through the freewheeling diode in this manner. Because we have taken the continuous load current, the current should not come to the zero. When the current is passing into the freewheeling diode, the voltage across the armature of a DC motor, nothing but a load, is equal to the voltage drop across this device. We have taken this device as ideal device, so the output voltage becomes a 0. Again, once the switch is on, again the source is connected to the load, the output voltage is equal to the VDC. Once the switch is off, now the current is passing from the load, freewheeling diode, return to the load. So the output voltage becomes a. During the freewheeling action, what physically happened means that previously there is some amount of energy will be stored in inductors. That energy will be taken by the motor itself. That's why we are calling it a freewheeling action. Now we are going to draw the output current. On the x-axis, we have taken the T. The output current is nothing but current which is passing at this point. When the switch is on, the current is changing from minimum value to the maximum value. When the switch is off, the current is changing from maximum value to the minimum value. Again, minimum value to the maximum value to the minimum value. This is the waveform of the load current. How this current is passing means in this interval, when the switch is on, this current is passing from the supply switch load again return to the supply. This current is passing through the freewheeling diode when the switch is off. Again, when the switch is on, this current is passing from the supply switch load again return to the supply. Again, in this interval, the freewheeling action is taken place, so the current will be passing through the freewheeling diode. Source is supplying a current to the load only when the switch is on. So, when the switch is on, The source current equal to load current. Nothing but in this interval the switch is on. So this current we have to take it as a source current. Same waveform. When the switch is off, the source current is come to the zero. Nothing but from this point to this point, the source current is zero. Again at this point, the switch is on. Source current equal to the load current. You take up the same waveform. Next, freewheeling diode current. The freewheeling diode current is nothing but the current is passing through the freewheeling diode only when the switch is off. Nothing but this current is nothing but a freewheeling diode current. So you take up the same current waveform here and the switch is off. Here also. This is a freewheeling diode. Here our interest is we have to find out what is the average output voltage. Area under the repeated curve. This is the curve which is repeating. This is the total time period T. So this area is nothing but so this is a rectangle T on into VDC divided by T. So the average output voltage V naught equal to VDC into T on, nothing but this area divided by the total time period T on plus T on. The T on by T is nothing but a delta, that is nothing but a duty cycle where delta equal to T on by. For a given time period, if we change the on period, so the delta value we can vary. We can vary the delta value from the 0 greater than the 0 and less than the 1. Variation of output voltage versus the duty cycle. Already we know the expression for the output voltage V naught equal to delta into VDC. We have taken the different values for the T on. Here we have taken the 3 values. When T on equal to 0, the delta value is 0, the output voltage is 0. When the T on equal to T by 2, nothing but half of the time period, then the delta value becomes a 0.5, the output voltage is equal to 0.5. We substitute this value here so that we are getting output voltage. When T on equal to T, then the delta value becomes a 1, so the output voltage is equal to VDC. So from this, we can say very easily that the output voltage will be vary from 0 to the VDC. You can control the output voltage below the input voltage. Calling this is a step down chopper also. Now we have to take the on the x-axis you take the delta, on the y-axis you have to take the output voltage. At 0, the output voltage becomes a 0. At 0.5, the output voltage becomes 0.5. Nothing but you are getting a point here. At 1, the output voltage becomes a VDC. You line join all these points, we are getting the straight line. From this graph, we can say very easily that by varying the duty cycle, you can get the different DC voltage which is less than the input voltage. If you use this converter between the DC motor and the DC supply, how the characteristics of a DC motor will be changes, that we are going to see. Speed torque characteristics of a DC motor with a DC to DC converter. We know the general expression for the speed torque relation, that is W equal to V by K minus T RA by K square for the shunt motor. This voltage is nothing but a armature voltage. This voltage is given by the DC converter. Already we know the expression for this. So V naught equal to V naught equal to delta into VDC. So in place of V, you substitute the V into delta VDC. Then we are getting the speed equal to delta VDC by K minus T into RA by K square. So the speed of the motor is highly depending upon the duty cycle. The duty cycle you can vary from 0 to the 1. Same manner, it is also depending upon the how much torque you are applying on the motor. The K is nothing but a motor constant. So on the x-axis you have taken the torque, on the y-axis you have taken the speed. Suppose if you take the duty cycle is a 1, the maximum amount of voltage will be given to the motor. So we are getting this is the no load speed. As the torque is increases, the speed will be decreases. This is the speed torque characteristics of DC motor when the delta equal to 1. Suppose if we take the delta equal to 0.5, the no load speed of motor will be decreases. As the load is increases, the speed will be decreases. The delta equal to 0.5. If further decreasing the delta 0.25, the no load speed of motor will be decreases. As the load on the motor is increases, the speed of the motor will be decreases. Suppose if the delta equal to 0, the motor runs at a 0 speed. Nothing but this converter is not going to give any voltage. These are nothing but a speed torque characteristics of a DC shunt motor for the first quadrant operation with the help of the DC to DC converter. So before going to close this class, let me summarize what are the points we have discussed. We have seen what is the meant by first quadrant operation. First quadrant operation is simply where the output voltage and current is positive. The load power becomes a positive, so the motor will be rotating in one direction. Next, we have seen the operation of the circuit and waveform of a DC to DC converter. This converter also nothing but a step down chopper. We have derived the expression of the average output voltage, that is V naught equal to alpha into Vc. So finally, we have seen what is the expression for the speed torque characteristics of a DC shunt motor with a DC to DC converter. And lastly, we have seen the characteristics of a DC shunt motor with a DC to DC. Thank you very much. If you have any doubt, you can ask me directly, or you can ask in the comment box of my YouTube channel, so that I am always available to solve all your questions.